Okay, this is probably going to be a long video, but I need you to understand something before you get into that, because some of you are so worried about your Math XL that you force your way through the video just to get to Math XL and get some information. But you need to understand this graphic that I just gave you so you can see the situation you're dealing with. Some of you are worried about your Math XL getting done, but remember your due date is like May 19th. Which means that there's no need to rush on those. Just make sure you understand the information, because what you are going to do every day is you are going to get closer to your test first. Which means that if you focus on Math XL right now and you try to rush through this video, you're not going to learn the information, which means you won't be able to do it on the test. What I told you also is that after you take the test, you are going to have one whole week of spring break to get everything done and catch up. So it's not like you want to do work over spring break, but if the situation just so happens to be that you need to use that to catch up, I don't think it'll take that long. And then of course we move towards the end of the year. But what I'm trying to tell you is don't rush your way through this video. Make sure you get it. This is where the actual money is earned for this test. Talking probability here, the scale of probability goes between 0 and 1. If someone tells you that something has a probability of 0, that means it's impossible. And if somebody tells you that something has a probability of 1, that means that it's going to happen. So just that's the range that we have. 0.5 of course would be 50%. You can do it as a percentage also. It means that it's halfway equally likely to occur. Decimals represent percentages. And so remember that if you get 0.5, you could say that that's 50%. Now we won't do that on our test, but in terms of multiple choice questions, if you get the answer of 0.5, you move the decimal over 2 spots, which turns into 50. If you get an answer of 0.03, you move your decimal over and you get an answer of 3%. So just real fast, something that has a probability of 0. It would be rolling a 6-sided die, which is just a 6-sided number cube, and getting an 8. So if I rolled one 6-sided die and got an 8, something is absolutely wrong. But something with a probability of 0 is rolling a 6-sided die and getting an 8 or getting a 7 or anything bigger than a 6, because of course you know on a standard 6-sided die it's only 1 through 6. So that is an impossibility. Just so you know, like I said, you need to kind of come up with your own for the test, or you can use that just so I understand that you know what it's something, or know what is an impossible probability thing. Write this probability formula real fast before we get started, which is number of successful results over number of possible results. What I end up writing is success over total, but I just kind of use that as my general idea. I will use that over and over, or I might even put S over T just so I have an idea on what I'm looking for, because in probability you want to slow down, just like I'm asking you to do for the video. You want to slow down and make sure that you get all the numbers you need that you're supposed to be getting. So in problem 1 it talks about, in a taste test 50 participants are randomly given a beverage to sample. There are 20 samples of drink A, 10 of drink B, 10 of drink C, and 10 of drink D. What is the probability of a participant not getting drink A? So remember again, probability means success over total. And so my first thing I want to do is find the number of successes. I do not, based off of this, it says I do not want drink A. That is a successful draw, not getting drink A. So drink A, I don't count that. Drink B is good, so I count 10. Drink C is good, so I count another 10. Drink D is good, so I count another 10. There are 30 successful draws in this problem. Again, drink A does not count because I don't want drink A, and so I don't count them, but I do count B, C, and D, which gives me 30 people. Total, how many total people were there, how many participants were there, how many drinks were there? That's usually somewhere in the problem. There are 50. And so you turn this into a decimal, which shouldn't be that tough, but 30 divided by 50 is 0.6, and that's that. That's all it takes. That is really all you need to understand. Again, you find your number of successes, you find your number of totals, you divide the two, you get your answer. But again, the trick is you have to understand that you are looking for successes and total. You put those in a fraction. Complement is the opposite, but it's a word game. The word complement is associated with the word not. And here's how you play the word game. If the word not isn't in the, or if the word not isn't found in the actual question, then you put it into the question or put it into the statement. If the word not is in the question, you simply take it out. So it's just a game over the word not. And look what it's looking for. It's looking for the probability of not getting drink A. Because not is there, we simply take it out, and we want the probability of getting drink A. That's it. Okay? So if the probability of this problem says not getting drink A, then we take not out and we say getting drink A. We simply flip it over. That is what a complement is. To find the probability of a complement, that means it's the exact opposite. Remember that the certain number is 1. So what we do is we say, well, if 0.6 is the probability of doing that, let's just take 1 minus 0.6, because of course that's the total amount minus what we have, and you end up with 0.4. Notice 0.6, which was this answer, 0.4, which was this answer, adds up to 100%. So 60%, 40% makes 100%. That is how you find a complement. That would be your answer. Okay? So again, the complement itself is just a game on the word not. We'll see that on a few questions. You just either take it out if it's in there, or you put it in if it's not in there, and then to find a complement, you simply take 1, the full number, 1 minus whatever your original probability was, and that gives you your complement. Alright. Another problem you're going to see. Student performed an experiment in which colored chip was randomly drawn from a bag and replaced. The table below shows the results of 50 draws. Find the probability of choosing a gold chip. Again, once I see the word probability, I think success over total, and I do my search. What am I looking for? I want a gold chip. So gold, no, 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 yes. I got 12 good picks out of this whole thing. Total, how many total picks do I get? Well, let's see. I think it should be 50, but we can always check. 9 plus 3 plus 11 plus 15 plus 12 does equal 50, so that would be my total. And then again, I simply divide that. 12 divided by 50, which should be 24, so 0.24 is my first answer to that. Notice how easy it is as long as you have the right idea, as long as you have the right strategy. Success over total, identify your successful picks, identify your total number of picks, divide the two, you get your answer. Again, what is the complement of this? Well, let's think about it. We wanted a gold, choosing a gold chip was our success. Was the word not isn't in there, so again what we do is we say not choosing gold chip. And that's all we have to do. Again, the probability here is of choosing a gold chip, so we put the word not in there and we say not choosing a gold chip. It's just a basic game you play on words. Get your practice, make sure you understand it whenever you get that there, because again, that is a test question you're going to see. What is the probability of this complement? Well, remember the complement is the exact opposite. Remember that these two things should add up to 1, so you do 1 minus 0.24 and you get 0.76 as your answer there. And again, notice if you took 0.24 plus 0.76, you get your full number of 1, which means that you did it right. Okay? So again, the complement itself is the opposite, and when you put the two things together, it should give you what you need on that. Number 3, you roll a standard number cube. Again, remember cube has 6 sides. I think people had issues with that in another class. Find probability of number less than 3. Success over total. First off, if you need to, list all the numbers. 1, 2, 3, 4, 5, and 6. And then I just circle the successful draws. Is 1 a successful draw? Is 1 less than 3? Yes, it is. Is 2 less than 3? Yes, it is. Is 3 less than 3? 3 is not less than 3 because it's equal. Of course, 4 is not, 5 is not, and 6 is not. And so my successful numbers are, there are 2 of them. Total numbers, there are 1, 2, 3, 4, 5, 6 of them. I divide those two, and I think we know what 1/3 is. 0.33 should be my probability there. What helps you out, and again, I know there are those of you who love to rush, what helps me out is that I actually list the numbers and I make my decision based off of looking at them, not thinking, because some of you are going to say less than 3. Okay, there's 3 of those there, and then you're going to go from there. That's going to mess you up, but just be careful. Describe the complement. Well, you want a number less than 3, so number not less than 3. That's it. That's the game. You want the complement of having a number less than 3. Don't say greater than 3 because that's not true, because greater than 3 still does not include 3. So just to keep it simple, the complement of having a number less than 3 is having a number that's not less than 3. Alright? And then if you want the probability of that complement, remember again that this and the other number should equal 1. So we do 1 minus 0.33, and you end up with 0.67. And again, if you took 0.67 and added 0.33 to it, you notice that you get your answer of 1, which means that this is obviously the right answer. Okay? Problem 4 says a survey is taken in which to determine which desserts are favorite students. I'm sorry, I was doing something else while I was reading. A survey is taken to determine which desserts are the favorites of students eating lunch in the Commons. If 55 students choose ice cream, 30 choose cake, 10 students say that pie is their favorite, what is the probability that a student's favorite dessert is not pie? Again, probability means success over total. I would start there every time, and that gives me the guide. We do not want pie as the favorite. 55 chose ice cream. That's good. We do want ice cream. 30 chose cake. That's good. 10 chose pie. We don't want that 10. We want 55 and 30, which is you don't want them to have pie. So yes, that's one. That's one. So 85 successful people in that survey. In terms of total people in the survey, 55 and 30 make 85, plus another 10 makes 95. And so all we have to do now is 85 divided by 95 and round to the nearest hundredth as usual. That 4 does not bump it up, so 0.89 is the probability there. It doesn't ask for the complement. I think you've seen enough of that, but the complement would be that the student's dessert is pie, because we would take the not out of there, and of course that complement probability would be 0.11, because that would make it equal to 1. But I just hope that that helps you to see what's going on. Experimental probability is the result of actual results. For example, what is the theoretical probability of flipping a coin and landing on heads? I actually could flip a coin 10 times. Let's see if I have one around. I guess I wasn't ready for this part. There it is. I'm lucky. So considering this, experimental probability just means let's actually see what happens. Theoretical probability says that the chance of me getting a heads is 50-50, and it says that I should have 5 heads and 5 tails when I flip this coin. So I'm going to flip this coin here. There's a tails. That's 1. Flip the coin again. You don't see it, but just so you know, it was tails again. I'm not cheating. I promise I won't cheat. Flipping the coin again, we get a heads. Flipping the coin again, we get a tails. Flip the coin again. Pretty much I'll stop once we get there, and just so you know, this was another tails answer, or tails result. That flip was also a tails. Sorry it was not on the screen, but just trust me. Again, I'm not going to lie to you. This is a heads flip. It's very hard to flip a coin into a small screen. And we have another tails. So just, we're not up to 10 yet, but remember that theoretical probability says that I should have had 5 over here, 5 over there. But without doing that, theoretical probability hardly ever happens. It's just something you use to make a decision. But notice that my experimental probability would not have matched theoretical 5 and 5. It would have gave me a different part there. So if this experiment was done again, I'm sure we'd get completely different numbers. We might get a lot of heads, not a lot of tails. You might get the 50-50 part. You might get 1 heads, 9 tails. You never know what you're going to get in terms of the experiment, but that's why it's called experimental probability. Whenever given an experimental probability, you can use that to predict larger experiments. So consider the following example. If a company tested 1,000 gadgets and found that 9 of them were defective, what is the probability of selecting a defective gadget? Again, probability is success over total. This is what we already did. We are looking for defective gadgets. We found that 9 were defective, so there are 9 to choose from out of 1,000. So we now do 9 divided by 1,000, and we get the answer of 0.009. Alright, that's the first part. But if the company ran a batch of 2,500 gadgets, how many of them would we expect to be defective? What we can do is say that if this is the experimental probability of picking a defective gadget, then we can just do 0.009 times whatever number that we actually have here, which is 2,500. So 0.009 times 2,500 means that we should have about 22.5 or 23 defective gadgets. That's it. Again, think about it. 9 out of 1,000. It should be 18 out of 2,000 because, of course, if it's 9 per 9. And then if you count half of that, half of 9 is about 4. And that would put you at 22 or 4.5, which is your 4.5. So using this number, that is how you use your probability in the actual problem. So if the experimental probability is 0.009, then take that times the number. If they made 4,000 gadgets, you would just do 0.009 times 4,000, and you could expect 36 of them to be bad. So again, that's how you deal with your experimental probability there. So just write this down for yourself in whatever form you need, but pretty much if you want to extend experimental probability, multiply the probability that you get by the number of actual items in the problem. So whatever number you're talking about there is what you're going to do. And we've got 2 more questions and we're done, so we're almost there. You ask 500 randomly selected households in town if they have a dog. Here's a point for experimental probability. If there are, like you see here, there's 24,000 households. If you really want to know how many households have a dog, you could walk around and randomly ask every single household, but think about how long it would take to ask 24,800 households if they have a dog, and then think about whether by the time you finish some of those households still had a dog or if their status changed. So what they do for experimental probability is you just take a small sample. That's what we call that, a sample. And using that sample we can kind of predict. Now it doesn't mean it's going to be accurate, but the bigger your sample, the more accurate you're going to be. So if we checked 1,000, it would be better. If we checked 2,000, it would be better. But just for the sake of saving time and getting it done, we did 500 households. 197 said that they do have a dog. Alright, it says if your town has 24,800 households, how many households are likely to have a dog? Well, here's what we do. First thing we do is we have to find out the probability of getting a dog. So success over total. 197 out of my experiment had a dog out of 500 people. So I do 197 divided by 500, oops, not 5,000, and I get the answer of 0.394. So there's about a 39% chance that the household has a dog. But I don't want 500 households. I want to know about all 24,800. And again, all I do is take that times the actual probability, which is about 39%. So I take 0.394, or 39% of, which means times 24,800, and I get 9,771.2, which means 9,771 households should have a dog out of 24,800. Alright. Describe the complement of this event. Well, if we are looking for households that have a dog, that means that do not have a dog. And what is the probability of that complement occurring? Remember, the complement is where I take the original probability and just subtract it for 1. So 1 minus 0.394 is 0.606. And the way I check that is I do 0.606 plus 0.394, and I should get the answer, which I do, of 1. Alright. Last question. Again, of the experimental probability. A manufacturer inspects 700 light bulbs and finds 692 of them work. Why do we do that experimental probability? Because would you like to have the job of testing 35,000 light bulbs? Instead, they just do 700 just to kind of check, and it's random. So you can kind of get a good guess from that. But again, 692 of them work. There are 35,400 in the manufacturer's warehouse. How many of those light bulbs are likely to work? So again, we are looking for those that actually work. So success over total. 692 is how many actually work. 700 was your total number of light bulbs. You divide those two numbers, and it's a pretty high chance, because I think you only missed 8. 0.99 is your probability there. But again, we're not talking about 700. We want to talk about 35,400, and we take that times the probability, and we get 35046. That's how many light bulbs should work. But if you think about it, if there are only 8 out of 700 that didn't work, there shouldn't be that many out of 35,400 that don't work, and that's about 400 that don't work, which makes sense. You want the complement of this event. That means that we are looking for the ones that are likely to work, so not likely to work. Again, it's just a word game. And then what is the actual probability? Well, if 0.99 is what we're talking about, I think it's easy enough to say 0.01 is going to be the complement, because 0.99 plus 0.01 adds up to 1. Outside of that, go to your Math Excel, do as much as you can, but again, make sure you are asking questions. Again, what I'm noticing is that some of you are so much working on your own that you're not asking questions, and if you don't get these questions answered by Friday, it's going to be a bad situation. You don't want to have 2 bad tests in there. So other than that, good luck.